All right, hello everybody. Welcome back to our conversation about chemical kinetics. In our last videos, we have explored the idea of the rate law, which is a relationship between the rate of the reaction and how that depends on the concentration of the reactants involved in this reaction. So when we talked about the rate law, we brought up this idea of reaction order, or the exponents that our concentrations of our reactant terms are raised to in the rate law. So what I want to do is I want to make a conceptual connection between these exponents, these orders, that goes a bit further than just relating them to the stoichiometry of the chemical reaction. Because again, fundamentally, when we're doing any kind of kinetic analysis, we are looking at experimentally driven models that we then work back from. So, like, this is what we expect, kind of in theory, but in reality, if we were to determine the rate law for some reaction, and thus get the orders of each reactant in that reaction, we would have to get that from experimental data. So let's talk about the meaning of reaction order, and I'll give you some examples of what that looks like. So the order of the reaction, these are the exponents in our rate law. And what the order of the reaction tells us is it describes how the rate depends on any change made to reactant concentration. So I have 3 reactions here showing different types of reaction orders. So let's look at this first one here. This is the reaction of NH3 going to nitrogen gas and hydrogen gas. And if we were to balance this stoichiometrically, we would have, let's see here, NH3, we would have 2 of these, so double this and then triple that. There we go. So if we were to look at this reaction and think about the order of the reaction with respect to NH3, we would predict, just from looking at the stoichiometry, that this would be second order. However, let's look at what's happening chemically in this reaction. So in this particular reaction that I'm showing you, we are looking at an adsorption reaction that is like the catalyst that allows for the dehydrogenation of ammonia, meaning like this reaction is catalyzed, meaning it's occurring on some kind of surface. So in orange here, we have the surface of the catalyst. And at every time we have an ammonia molecule that makes it to this surface, that catalyst allows for the dehydrogenation, which then ejects as decomposition products through desorption N2 and H2. So what does it mean to be zero order? Like, why is this an example of zero order reaction? Let's think about what is going to affect how many times we can have an ammonia molecule become dehydrogenated. So if we think about this particular reaction that is catalyzed, we will see that since the reaction depends on the surface area available of the catalyst, the concentration of ammonia that could be present in the surrounding environment, so I could have ammonia here, 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 right? I can up the amount of ammonia, is fundamentally not going to affect how fast this dehydrogenation happens, because what is limiting how fast this reaction happens is the process of the ammonia making its way through adsorption to the catalyst site. So because this is a surface area dependent reaction, the concentration of ammonia doesn't affect the rate. Because if we add more ammonia or take ammonia away, we're still fundamentally not changing the surface area of available catalyst surface on which the reaction happens. So this would be zero order. So zero order concentration doesn't affect the rate. In this next example, we are looking at the severing of sucrose into glucose and fructose. This is what happens via digestion. This is hydrolysis, I believe, water cutting. So water comes in and then boom, creates OH groups on both of these sugars. So the hydrolysis of sucrose. Okay, so let's take a look at this reaction and what is going on. This is not a surface area dependent reaction. This is just, do we have an encounter between like a sucrose molecule and then any of the surrounding water molecules that are like ever present in the body, in the stomach. And if we were to increase the amount of sucrose that were present, then we would increase the amount of products, glucose and fructose, resulting from that hydrolysis. And that kind of relationship is a direct proportionality. So we would say that as we increase the amount of sucrose, the rate of hydrolysis increases. So this means that we are first order because there is a direct dependence or proportionality of the rate on the concentration of sucrose. So direct dependence, if I were to double the amount of sucrose in the stomach, then the rate would also then double. Direct proportionality. And then lastly, we have this complexation reaction. So this is cisplatin, which complexes with water to form the hydroxylated version. And this reaction does require, in stoichiometry, one cisplatin molecule for every one water. So it's not like the case up here with the sucrose, where we're surrounded by like a bunch of water molecules and they're just like around and available. Here, this reaction requires absolutely one water in order for us to then create these new, we call them ligands, additions onto the cisplatin molecule. So since we have two reactants that are required to make the products happen, then we call this a second order reaction. So we would say that the rate is highly sensitive to concentration of reactant. Specifically, it is in a square relationship. So if I were to double the amount of cisplatin, my rate would then quadruple, right? Because 2 raised to 2 is 4. This is what we call zero order reaction. Sorry, not zero, second order reaction. Which means that in our term in our rate law, we would have an exponent of 2. So some various reactions. Depends on surface area. One reactant molecule implies first order. 2 reactant molecules implies second order, etc. So how is this useful, and how can we determine the reaction order and then the reaction rate law given some kind of kinetic data? So anytime we are asked to determine the rate law, we are asking ourselves, how does the reaction rate change when the concentration of either reactant changes? Because if it changes in a direct proportionality, that means we are first order. If it doesn't change at all, then that means we're zero order. And if it changes in that square manner, then that means we're second order. So we need to look at information like, okay, here we have a bunch of rates, we've got a bunch of concentrations, meaning this reaction was performed 4 different times with 4 different reaction mixtures, and the initial rate, so early rates of reactions, were observed. And we need to compare trials that allow us to figure out, how do we have a dependence on X and how do we have a dependence on Y? So how do we depend on both of these reactant concentrations? So here, kind of making this question a little bit more specific, how does this rate depend on concentration X and concentration Y? So let's start with dependence on the concentration of X. This is where we're going to look for some kind of change in the concentration of X, but we're going to control or keep constant the concentration in Y. Because if we change both X and Y, then the rate's going to change in a way that we don't know is like directly because of what thing, right? We don't know if it's X that's responsible for changing the rate. We don't know if it's Y that's responsible for changing the rate. So we need to look at like just one. So let's look at changing X, but keep the change in Y constant. So where can we find information like this? Like, is there a trial where the amount of X is changing, but Y is not changing? So let's see here. We've got trial 1, they're both 1 molar. Trial 2, they're both 0.5. So we had a change here in X and a change here in Y. So we cannot compare trials 1 and 2. I could look at, let's try 2 and 3. Okay, this does show a change in X, which is good. And oh, hey, this shows no change in Y. So I'm going to compare trials 2 and 3. So let's describe what happened when X changed, but Y didn't change. So first of all, let's look at how X changed. So the concentration of X went from 0.5 molar to 1 molar. This didn't change at all, so that should not have reflected any kind of change in the rate. But let's see if there is a change in the rate that is related to this change in the concentration of X. So we can say that the concentration of X doubled And then as a result, how did the rate change? So 1.48 times 10 to the negative 3 to 2.96 times 10 to the negative 3. I'm going to go ahead and take the quotient of those two, meaning I'm going to divide them. That's how I can compare them. I could be lazy if I wanted to. I could round this up to like 3-ish and round this up to 1.5-ish, and that would then be doubling, but let's prove it to ourselves. So 1.48 times 10 to the negative 3 over 2.96 times 10, yep, when I do that, I get exactly a 2-to-1 ratio. So when my amount of x is doubled, the rate is also doubled. So if my concentration changed, affecting the exact same kind of change in the rate, then that means there's a direct proportionality between our concentration of x and our rate. And what did we say that meant here? Direct dependence of rate on the concentration. We call that first order. So we have to be first order with respect to x. So WRT with respect to x. Okay, let's do a similar treatment for y. So here we had as x doubled, the rate doubled. Now we're going to look at y. So let's find some trials where x is held constant. So it looks like here and here, but y is changing here and then here. So we're going to compare trials 1 and 3. So let's look at what happened here. Trial 1, again, x is constant, and we want to figure out then, like, since this is not going to have any bearing on our rate, what the amount of y is going to do to our rate. So in this case, we cut y in half. So concentration of y was halved. And let's see what kind of effect that had on the rate. So the rate was initially this. And now we need to look at this here. So we have 1.184 times 10 to the negative 2. Let's compare. And we are going to compare that just by taking a ratio to the 2.96 times 10 to the negative 3 molar per second rate. Okay, when I do that, I get a 4-to-1 ratio, meaning that when y was halved, notice this is a bigger number, this is a smaller number, 4-to-1 ratio. This means that the rate decreased by 75%, or the rate was cut into fourths, if you want to think about it that way. Decreased by 75 or 20. Let's not think about it in terms of percentages. I think I want to say 25%. So rate decreased by 4, meaning 1/4 times the rate. The rate is 4 times less large. Okay. So let's think about this. 1/2 resulted in 1/4. How do these two numbers relate? Well, wait a minute. Isn't 1/4 simply 1/2 squared? So since we had this square dependence of the rate, on the concentration of Y. This would then be second order. So as Y was halved, the rate decreased by 4, where specifically we recognize that a change in 1/2 affecting a change in 1/4 is squaring that 1/2. So because we have this square here, we are going to call this second order. Sorry, I'm trying to get my color coding down. This should be purple. So this reaction is second order with respect to Y. Okay. So just by like looking at this data and asking ourselves this question, how does the reaction rate change when the concentration of each thing is individually changed? We were able to determine how the rate depends on either reactant independently. So we know that if we were to change the concentration of X and keep everything else constant, then the rate would change the exact same way that X concentration changed. Whereas if we were to change the concentration of Y and keep all else constant, then we would see that we have a second order dependence or a square relationship between our rate and our concentration Y. Okay, what do we do with this? What is the rate law and not the equilibrium, the rate constant, lowercase k for this reaction? So recall the rate law has structure R is equal to K, concentration reactant, raised to the M, times reactant 2 raised to the N, where M and N are the order. So we had the reaction X plus 2Y goes to Z. And we found that X was something that directly affected our rate. So we say that the reaction is first order with respect to X, and we saw that Y was something that had a square effect on the rate. So this is second order. This is kind of nice and tidy for us because it does match the stoichiometric, like we call it the molecularity of this reaction. So let's rewrite this. We have now the rate is equal to the rate constant K times concentration X raised to the first, to say that we're first order. And then times concentration Y raised to the second order. So this is our rate law, though this rate law is incomplete. This leaves like the structure of the rate law intact, but it does not give us the value of the rate constant. So in order to find K, what we need to do is use the rate data given to find K. So normally you would do this for all trials and then average it. We're going to just choose one trial. So since we've already looked at trials 1 and 2 and 3, let's perhaps look at trial 4 just because we haven't used it yet. So we're going to use trial 4 data. So we have R is equal to K, concentration of X, concentration Y squared. The rate in trial 4 is 2.96 times 10 to the negative 3. That's equal to K times the concentration of X in trial 4, which is 0.250, times the concentration of Y, which is 1 squared. which means that K is equal to 2.96 times 10 to the negative 3, mathematically over 0.250. I am going to keep my units because let's see here, 1.0 squared, that's 1.0 molar squared, and then 0.250, that's molar, so this is molar cubed in the denominator, and the rate is always molar per second. So let's get this number, pulling out the calculator. So we have 2.96 times 10 to the negative 3 divided by 0.250. We get a value of K, over here, K is equal to 0.01184. And let's think about our units. We've got molar, this will cancel here, become molar squared. So this becomes inverse molar squared and inverse time. So now my full rate law which includes the value of K, says the rate of this reaction is equal to 0.01184 inverse molar squared, inverse seconds, times concentration X, times concentration Y squared. This is the experimental rate law as determined from experimental data. And it just so happens in this case that this tends to agree with like the stoichiometric model of our reaction. But that's not always true. Okay, so this was some more practice on determining the rate law and understanding the nature of reaction order. In our next video, we are going to move on to different ways of modeling the reaction rate. Because if you notice in this conversation about the rate law, we're looking at just how concentration affects the rate. But again, when we're talking about the rate, we have this temporal or time-related component that's important, right? A rate is a change in concentration over time. So in our next series of modeling chemical kinetics or the rate of reaction, we're going to figure out not just how rate depends on concentration changes, but also how those concentration changes can be monitored over time and what that means with respect to the order of each reactant in our reaction. So coming up, modeling chemical kinetics using integrated rates. See you then.